Welcome to our paper presentation, which is entitled Performance Optimization of Cluster-Based MAC Protocol for VANETs. It is published in IEEE Access in September 2020. Recently, vehicular ad hoc networks have garnered interest for intelligent transportation system and automation. VANETs not only increase road safety and efficiency of transportation, but also enable autonomous vehicles to be implemented more rapidly and efficiently by reducing reliance on expensive sensor suites. VANET enables communication between vehicles to vehicles and vehicles to infrastructure. VANETs support a lot of applications which are classified as safety messages and non-safety data. Lane changing assistant, emergency warning, accident prevention, warning for traffic sign or signal violation, indication of the emergency electronic brake light, road condition, etc. are safety messages. Map update. Traffic information system, web browsing, weather information, gaming, location and price information of gas station or restaurant, content distribution, etc. are non-safety data. MAC and physical layer specifications are outlined in the IEEE 802.11 standard, which incorporated the IEEE 802.11p standard. Due to relative mobility, topology changes rapidly with frequent link breakage in VANETs. Therefore, communication becomes unstable. Moreover, for safety or crucial communication, safety message has priority over non-safety data. Safety message is time-dependent and should not experience delay more than 100 milliseconds. However, both IEEE 802.11p and IEEE 802.11 cannot fulfill the 100 milliseconds delay requirements. There is no existing protocol that can fulfill the requirements. In this project, a novel cluster-based MAC, CB-MAC, protocol is presented for VANETs. The cluster formation process is defined. Cluster head, CH, election and cluster merging processes are described for efficient communication in the cluster as well as out of the cluster. The mechanism defined in IEEE 802.11 standard is specially designed for only direct communications and is not suitable for cluster-based communications. Therefore, new control packets are introduced, and the existing control packet format is modified to support cluster-based communications. For effective MAC protocol design, the request to send, RTS, clear to send, CTS, mechanism is not used for safety messages which are of broadcast nature. On the other hand, the RTS-CTS mechanism is used for non-safety data delivery to eliminate hidden node problem. Moreover, cluster size affects performance of CB-MAC protocol. Since channel contention, probability of collision, packet loss, etc. depends on cluster size, i.e. vehicle number in cluster, performance depends on cluster size. If the cluster size is too large, performance decreases significantly because there will be a large number of packet collisions when the number of vehicles is too high. Alternatively, a small cluster could not use existing radio resources because of the insufficient number of vehicles, i.e. cluster members, CMs, in the cluster. Therefore, performance of CB-MAC protocol is also optimized by optimizing transmission probability based on cluster size. Markov chain model-based analytical model is presented to explore the performance of CB-MAC protocol. The proposed protocol is validated by numerical studies and simulation results. The model of microscopic mobility is generated in simulation of urban mobility, SUMO, then the output of SUMO is used in MATLAB as input and simulation results are achieved. The numerical results exhibit that the CB-MAC protocol improves system performance and satisfies the delay constraint of 100 milliseconds for safety messages and ensure quality of service. Simulation results prove that performance of CB-MAC protocol is optimized. Vehicles traveling in the identical direction will be in the same cluster because clustering with moving vehicles in different direction causes signaling overhead due to frequent reclustering. Therefore, clustering mechanism of CB-MAC protocol is stable. Figure presents the finite state machine of CB-MAC protocol. If cluster head wants to broadcast a safety message, it will broadcast immediately. If a cluster member has a safety message to transmit, the cluster member will send to the cluster head through RTS-CTS handshake. If cluster head wants to transmit a non-safety data, it will unicast the non-safety data directly. If a cluster member has a non-safety data to transmit, the cluster member will transmit to the cluster head using RTS-CTS handshake. The performance of CB-MAC protocol is optimized by optimizing transmission probability with cluster size for both safety messages and non-safety data. To achieve optimized performance, each vehicle should adopt the optimum transmission probability in the cluster, which can be obtained by tuning the number of clusters in the VANET. Therefore, optimum number of clusters is defined based on number of vehicles in VANETs. Throughput, packet dropping rate, PDR, delay expressions are derived. Then optimization is done by optimizing transmission probability in the cluster, and the optimum number of clusters can be obtained. The performance of the optimized CB-MAC protocol is examined and analytical study is verified through Monte Carlo simulations. Table provides value of parameters utilized in simulation. Simulation results are conducted in SUMO and MATLAB. Firstly, microscopic mobility model is produced in SUMO, then output of SUMO is used as input to MATLAB. Simulation results are achieved by 1000 Monte Carlo iterations. In this study, practical mobility parameters are taken from SUMO, which makes the analysis realistic. Figure shows throughput versus number of vehicles. The throughput of optimized CB-MAC protocol is better than both traditional MAC and CB-MAC protocols. Figure presents packet dropping rate against number of vehicles. PDR of proposed optimization mechanism is lower than the CB-MAC and traditional MAC protocol, which makes communication more reliable. Figure demonstrates average packet delay against number of vehicles. The delay for optimized CB-MAC is less than CB-MAC and traditional MAC. Thus, CB-MAC has lesser delay than traditional MAC, and CB-MAC protocol satisfies the strict delay constraint of 100 milliseconds for safety messages. Optimized CB-MAC limits channel contention more efficiently than CB-MAC protocol by optimizing cluster size, which results in lower delay than CB-MAC. Here is the paper link and citation text. Thanks for watching.